So what is replacement lemma? I won't formally write it as a theorem and so on. I'll give you the proof. You can read it anywhere. Okay. So let's look at what is known as a replacement lemma. Okay. So the idea is this: suppose I have this set of vectors Vn, okay, be a basis, okay, vector. You have a basis vector, okay. That means I give me any vector V, basis vector of let's say vector space V. Now we take any vector V in V, I can write it as a linear combination of V1 through Vn, right? That's the definition. Now, is it possible to replace V1 through Vn by some vector V? That's the question, right? So can we replace, I'll take off one vector V1 and replace it with V, and still I should be able to manage to get the entire whatever vector space, right? Is it possible? So let's see. Okay, so let's take a vector, some vector V belonging to V not equal to 0. Okay, so suppose I take a non-zero vector. So what is the first thing that you can do? So I can write V as linear combinations of bases. Do you agree? Is this clear? I take a non-zero vector, I can always write. Okay. Well, even zero vector trivially I can write, but this is non-zero. Okay. So I can also assume that without loss of generality, alpha 1 is not 0. Right? Suppose then you may argue that V can be V2 itself, then alpha 1 should be 0, alpha 2 should be 1, right? But then I can rearrange or re-index and make sure that the first V1 is the vector, right? So without loss of generality, let alpha 1 not equal to 0. Okay, is this clear? Now what I will do is let's see what happens to, let's check what kind of vectors. Let's say V, V2 and so on Vn are. What kind of vectors, meaning are they linearly independent? Will it span all these questions, right? So what do you think? So do you think these are linearly independent? Do you think these are linearly independent? Yes or no? Remember, this is very crucial. Okay, so this alpha 1 is not 0. Okay, fine. So now what can you say? So can you claim that these are linearly independent? Huh? No or yes or no? Huh? So pictorially, let's look at. So for example, you have, let's say, V1 and this is V2. Of course, these two vectors form a basis for R2, right? Do you agree? So now I'm going to give another vector. Okay, so maybe this is my vector V. Definitely alpha 1 is, maybe I should write it the other way. Okay, so write it as V2 and V1. So of course, I should walk some non-zero distance along V1 and some non-zero distance along V2 to get to V, right? Therefore, alpha 1 is not 0 in this case, right? Now, naturally, I can replace this guy by this guy, right? So I can take V1 and V2 and V as my new basis, right? Without any problem. Do you agree with this? So you cannot do that provided this V aligns with this or this. Okay, then only we cannot do. Otherwise, we can, right? You agree? That's what it says. So I'm going to replace with such a vector with the first one, V1. Okay, so the claim is, or intuition, or the picture says that this particular thing is also linearly independent and it spans the entire vector space. In other words, they form a basis. Okay, so how do you prove this? Proof is kind of interesting. Okay, so maybe in the core of data analysis or machine learning, you don't need this, but it's a cool trick which is useful in general. Let's look at that. So what is it that I have to prove? I have to prove that this vector V, V2, V3 and so on, Vn form a basis. First of all, let's prove that it's linearly independent. So what is it that I have to do? So if I have to prove that, need to show that If I take linear combination of these vectors and equate it to 0, then the coefficient should be 0. That's what you mean by linearly independent, right? So alpha, let's look at this. Okay, so maybe I'll use a different beta 1 times V plus beta 2 times V2 plus beta 3 times V3 and so on, right? So I'll write it in short form. So this is I equal to 2 to n beta I Vi equal to 0 implies beta I equal to 0 for all I. This is what we need to show, right? So how do you show this? Any idea? But what is V? What is this guy? V is such a vector that I can write it as a linear combination of V1 through Vn, because V1 through Vn form a basis. So I can write that, right? So I equal to 1 to n alpha I Vi. Okay, so let's say some coefficients alpha I. Remember, alpha 1 is not equal to 0. That is crucial. Okay, so now if I plug that in, what do I get? I get beta 1. So let me write it like this. So I'll say I equal to, let me start with 2, okay, 2 to n, okay. Alpha I Vi comes from here and there is a beta 1, right? So beta 1 alpha I Vi, okay, this is fine. Then I equal to 2 to n beta I Vi, that comes from this, plus I have to write the first term. What is the first term? Beta 1 alpha 1 V1, right, equal to 0. So, well, if it is equal to 0, what does that imply? That implies, well, let me write it like this: beta 1 alpha 1 V1 plus summation I equal to 2 to n beta 1 alpha I Vi equal to 0, right? So now what can you argue out now? So can somebody argue out beyond this? What is it that you will get? Yes. What can you say from this equation? Can somebody tell me? If you don't speak, then even I'll get bored, right? Can somebody speak? Online?
So they are linearly independent.
What are linearly
No,
independent?
no, sorry. The vectors v1 2. No, if sorry, that's wrong. That's wrong.
No, you are right. V1 through Vn are linearly independent because it forms a basis, right?
Yeah, they are the basis.
So what can you say about this equation? It's a linear combination of V1 through Vn. So that means what? All the coefficients should be 0, right? So this implies, okay, let me write it here. So this should be equal to 0. These should be equal to 0, right? Do you agree? Right? So did I make any mistake? V1 and this is, yeah. So did I make a mistake? So this is not, oh my God. So this is not correct, right? So what is this? Did I make a mistake here? So there are two terms, right? Beta 1 alpha I plus beta I times Vi. Okay, so this is a mistake, right? Algebraic mistake. So I have to add this to beta I because Vi's are common, right? Is that clear? Fine. So this is also 0. So what does this imply? So of course beta 1 times alpha 1 is 0. But what can you say about alpha 1? Alpha 1 cannot be 0.
Not 0.
Right? Therefore, what can you say from this? This you can say beta 1 is 0. Do you agree? So if beta 1 is 0, of course, all these terms will be 0, right? Do you agree? So now, beta 1 alpha I plus beta I. Beta 1 alpha I plus beta I is 0. But beta 1 is 0, which implies beta I is 0 for all I, right? So that's what we wanted, right? Beta 1 is 0, beta I is 0 for all I, greater than or equal to 2. Well, the previous one says that it should be greater than or equal to 1 also, because beta 1 is also 0. That means they are linearly independent. Is this clear? Okay. Okay, so I don't bore you too much with the other proofs. So the second claim is you should check this whether this is true or not. V2 to Vn span V. Okay, you check this. Okay, I won't help you in this. So you just figure out how to prove this. Is that fine? So that means if I have a basis, if you have a vector V not equal to 0, I can replace one of them by that vector. Okay, that's what it says, right? Now let's go back to what we did in the last class, right? So we had to prove that the dimension is unique, right? So you cannot have dimensions being different for the same space, right? So how do you prove that? You take two bases, let's say V1, V2, etc., Vn, and similarly you take U1, U2, etc., Um, M greater than N. Okay, this is the case. Both are bases. Okay, so what do you mean? How do you use the replacement lemma, the previous argument? What do you do? What should I replace this with? Huh? Right? It says I can replace one of the vector by the other and still maintain the basis. So now, how do you prove that you cannot have M not equal to N, right? So what do you do? I mean, I'll just show pictorially. First thing is I can take U1 and replace with one of them, right? I can put U1 in one of them and replace, knock off some Vi. Okay. Take U2 and knock off something here, right? Keep on doing that until Un, right? So you knock off. So what will happen? You would have knocked off everything here and replaced with N vectors among M vectors. Okay. But now see what the previous theorem says. It says even if you replace, it still obeys the property of basis, right? Linear independence and span. But now you have taken a smaller subset of a basis and you are claiming it's a basis, which is a contradiction, right? So you cannot have that. So that means the only possibility is you should have exhausted everything. That means M equal to N. Okay. So is this clear? Any questions? Okay, fine. Everything fine? Okay.